In the name of Almighty God, I am Master Sankoshi, and today I want to talk about microwave plasmas. Microwave plasmas, also known as wave-heated discharge, are sustained when electrons gains energy directly from an electromagnetic wave as it penetrates into the plasma. The behavior of a microwave plasma depends significantly on the mode of the electromagnetic wave, either TE or transverse electric or TM transverse magnetic. In two-dimensional axisymmetric models, the TE or transfer electric mode involves computing only the azimuthal component of the electric field out of plane, while the transverse magnetic mode involves computing the radial and axial components in plane of the electric field. These differences lead to distinct electromagnetic field distribution and energy deposition profiles. Regardless of the mode, electromagnetic waves cannot propagate into regions where the electro density exceeds the electrical value. At the critical electron density counter, the wave transition from the propagating to evanescent, meaning that it decays exponentially instead of transmitting energy further into the plasma. As a result, all the wave power is absorbed within a very thin layer, which can lead to a strong localization of heating. The operating pressure for microwave plasmas spans a wide range. For electron cyclotron resonance or ECR, plasma pressures are typically 1 Pascal or lower. For non-ECR or electron cyclotron resonance microwave plasmas, pressure usually range from 100 Pascal to atmospheric pressure. Power levels can also vary greatly from just a few watts to several kilowatts depending on the application and plasma configuration. This figure shows electron number density isosurfaces in logarithmic scales and electric field norm in a microwave plasma torch operating at 2.45 GHz with an input power of 50 watts. The next chapter is the dielectric barrier discharge. Dielectric barrier discharge or DBDs are used in a variety of applications, including ultraviolet and extreme ultraviolet UV light sources, ozone generation, and surface modification. The fundamental operating principle of a DBD involves a gas filled gap between typically two dielectric covered electrodes. A time varying voltage is applied to one electrode. As the applied voltage increases, the electric field within the gap strengthens. Free electrons present in the gas are accelerated by the field, and if the field is sufficiently strong, they can gain enough energy to ionize natural gas molecules. This initiates an avalanche effect, rapidly increases the electron population on a non-second time scale. During each voltage cycle, free changes accumulate on the surfaces of the dielectric barriers, effectively shielding the gap from the applied electric field. This accumulation suppresses further ionization and can lead to temporary plasma extinction until the applied voltage reverses polarity and the process begins again. The electric barrier discharge typically operate in the pressure range of 0.1 to 3 atmosphere with an applied voltage of 1 to 100 kilowatt and a frequency of kilohertz up to megahertz. Space distribution and temporal evolution of the mass fraction of electronically excited argon atoms in a dielectric barrier discharge driven at 50 kHz with a sinusoidal voltage amplitude of 750 volts at 1 atmosphere pressure. The x-axis represents space and the y-axis period fraction. The chapter of plasma enhanced chemical vapor deposition. Plasma enhanced chemical vapor deposition or PECVD is widely used plasma assisted thin film deposition technique that enables the formation of high quality coating at relatively low substrate temperatures. By utilizing reactive plasma species generated from the precursor gases, plasma enhanced chemical vapor deposition or PECVD facilitates enhanced chemical reaction on the substrate surface, resulting in improved film properties. Modeling PECVD processes requires capturing the complex interplay between plasma dynamics, gas phase chemistry, surface reactions, and transport phenomena. The plasma module provides comprehensive tools to simulate these coupled physical and chemical processes, enabling detailed analysis and optimization of PECVD reactor performance. Variation of silicon deposition rate along the wafer with silane mole fraction in an inductively coupled plasma reactor using a silane argon mixture at 13.56 MHz and 50 watt is inside this plot. The y-axis shows radius based on centimeter, and the x-axis is represents radius based on centimeter, and y-axis represents the position rate based on uh, um, the the minutes, or the distribution based on the minutes. Plasma enhanced etching. Plasma enhanced etching is a critical plasma assisted process widely used in microfabrication to selectively remove material from a substrate with high precision and anisotropy. This technique leverages reactive plasma species such as ions, radicals, and neutral particles to chemically and physically etch target surfaces, enabling the fabrication of intricate micro and nano-scale features. Accurate modeling of plasma enhanced etching involves capturing the complex interactions between plasma chemistry, surface reactions, ion bombardment, and transport phenomena within the reactor. The plasma module offers advanced simulation capabilities to analyze and optimize these processes, providing valuable insights into etch rates and uniformity. This figure shows number density and flux streamlines of CF3 ions in an ICP reactor with an radio frequency bias of 100-volt amplitude. The color scale on the streamlines represents the magnitude of the CF3 positive flux. Equilibrium discharge. Equilibrium discharge, also known as thermal plasmas, have a wide range of industrial applications, including cutting, welding, thermal spraying, waste destruction, and surface treatment. These plasmas are typically assumed to operate under partial to full local thermodynamic equilibrium conditions. Under LTE or local thermodynamic equilibrium, the electron temperature is equal to the temperature of the background gas, and the plasma behaves like a conductive fluid mixture. As a result, thermoplasmas are modeled using the magnetohydrodynamics or MHD equations, which treat the plasma as a continuum governed by fluid dynamics and electromagnetic interactions. Unlike non-equilibrium plasmas, equilibrium discharge don't require computation of the detailed chemical composition. Instead, the focus is on solving for gas temperature and electric fields. This modeling approach enables more efficient and numerically stable simulations, particularly when estimating thermal loads on surfaces, a critical factor in many industrial processes. Here in this figure illustrates fluid velocity in an atmospheric pressure thermal plasma torch operating in a at 11 kilowatt. And this figure illustrates temperature, its surfaces, and fluid velocity magnitude streamlines in an atmospheric pressure direct current arc operating in air at 80 ampere. You see there are two legendary bars, one related to temperature based on Kelvin, another is related to velocity based on meter per second. Plasma modeling is typically approached using one of three methods: kinetic, fluid approximation, or hybrid. Each method involves solving an appropriate transfer equation in conjunction with Maxwell's equations. The first one is the kinetic method solves for the distribution functions of ions and electrons using the Boltzmann equation. Alternatively, a Lagrangian approach may be used where ordinary differential equations describe the motion of individual particles as seen in particle in cell or peak simulations. This method allows the electron energy distribution function to assume any shape in energy space and captures non-equilibrium effects that fluid models may miss. However, it is computationally intensive and poses challenges in handling complex plasma chemistries. The next is that in fluid models, the plasma is described in terms of macroscopic quantities. This is done by checking velocity moments of the Boltzmann equation, resulting in a system of cupped partial differential equations that can be solved using a finite element method. The plasma module uses this approach. Advantages of the fluid approximation includes computational efficiency, ease of incorporating complex plasma chemistries, and straightforward coupling of electron dynamics with electromagnetic fields, which also computed using the finite element method. The last one is hybrid models combine aspects of both kinetic and fluid approaches. Typically, electrons are treated kinetically via the Boltzmann equation or Monte Carlo methods, while ions and neutral species are modeled using fluid equations. This approach balances the high accuracy of kinetic models with the lower computational cost and flexibility of fluid models. And the chapter of physics guide. Plasma modeling is inherently complex because it integrates concepts from the reaction engineering, statistical physics, fluid mechanics, physical kinetics, heat and mass transfer, and electromagnetics. This creates a true multiphysics challenge characterized by intricate coupling between these various physical processes. The plasma module is designed to streamline the setup of self-consistent models for low temperature and LTE plasmas. The physics interfaces provide all the essential tools to simulate plasma discharge, starting with a Boltzmann equation two-term approximation solver. This physics interface calculates electron transport properties and source coefficients based on a set of electron impact collisions cross sections. Using this interface, many key discharge characteristics can be predicted by inputting parameters such as the electric field and electron impact reactions that define the plasma chemistry, all without needing to solve a space-dependent problem. For space-dependent models, the plasma chemistry comprising reactions and species is conveniently managed within the model builder. When fluid velocity and gas temperature are relevant, dedicated physics interfaces for laminar flow and heat transfer are available. Additionally, several options exist to couple charge species transport with electromagnetic fields, offering flexibility in modeling the plasma environment. We want to go through the physics interface list by space dimension and preset study type. Physics interface, the ACDC, and this is there are two different AC/DC physics interfaces. The first one is electrical circuit, and the icon you see it's a AC/DC thunder, and also one we have a ground and two other elements from which is a diode and capacity, and the tag is CIR, space dimension not space dependent, and available study type is stationary frequency domain, time dependent frequency domain, eigen frequency. The next one is electrostatics, and the tag is ES, is working for all dimension, and available study type are stationary, time dependent, stationary, source, sweep. In the fluid flow branch, there is a sub-branch, single-phase flow, and laminar flow, SPF, or single-phase flow. It's working for three-dimension, two-dimensional axisymmetric, and available study type is stationary, time-dependent. In the plasma branch, there are different and various interfaces. Boltzmann equation two-term approximation is working for zero dimension, and available study type is mean energies, reduced electric field, time dependent. The next one is plasma time periodic, and the tag is PTP and working for one-dimensional, two-dimensional axis symmetric. And available study type is time periodic to time dependent. The next one is plasma, and the tag is plus, working for all dimensions, and available study type is time dependent and stationary. Again, there are more three different physical interfaces. Industrial cupped plasma, space dimension is working for three and two-dimensional, and also two-dimensional axis symmetric, and available study type is frequency transient and frequency stationary. The next physics interface is inductively coupled plasma with a radio frequency bias, and is working for two-dimensional and two-dimensional axis symmetric. Then available study type is frequency time periodic, time dependent, and the physics interface is microwave plasma. It's working for three-dimensional, two-dimensional axis symmetric, and available study type is frequency transient. The next branch is non-isothermal plasma flow. We have a plasma non-isothermal flow, two-dimensional, two-dimensional axis symmetric, and available study type is time dependent and stationary. The next one is inductively cooled plasma, non-isothermal fluid, and it's working for three and two-dimensional axisymmetric, and available study type is frequency transient and frequency stationary. The next one is microwave plasma, non-isothermal fluid. It's working for three-dimensional, two-dimensional axisymmetric, and available study type is frequency transient. And the next one is plasma time periodic non-isothermal fluid. It's working for two-dimensional axisymmetric, and available study type is time periodic to time dependent. The next physics interface is inductively cooled plasma with radio frequency bias, and its non-isothermal fluid is two-dimensional axisymmetric, and available study type is frequency time periodic to time dependent. And the branch of equilibrium discharge. Under this branch, there are three various in a physics interface: equilibrium discharge, out-of-plane currents, and it's working for two-dimensional axisymmetric, and available study type is stationary time-dependent, frequency transient, and frequency stationary. The next physics interface is equilibrium discharge in plane currents, and it's working for two-dimensional axisymmetric, and available study type is stationary, time-dependent, frequency transient, frequency stationary. And the next one is equilibrium discharge, and it's working for three-dimensional, and available study type is stationary, time-dependent, frequency transient, and frequency stationary. And or another physics branch is a species transform, and physics interface is drift diffusion, and the tag is DD, and it's working for all dimension, and available study type is time dependent. Under the species transport, there are different physics interfaces. Also, heavy species transport, the text is HS, as abbreviated from the heavy species transport, is working for all dimension. Available type is time dependent. Another physics interface is charge transport, and the abbreviation is CT, working for all dimensions, and available study time is stationary. Another one is coronal discharge. It's working for all dimensions, and available study type is stationary. Another physics interface is electrical breakdown detection, and the abbreviation is EBD, and it's working for two-dimensional axisymmetric, and available study type is time dependent. So we have some notes that the first notes that we had one on, for example, this electrostatics, we have, or this laminar flow, we have a notes, and for these two we have a notes that this physics interface is included with the core computer package, but has added functionality for this module. And the two which I can show you is non-isothermal flow, requires the addition of the ACDC module, and the three requires the additional of radio frequency module, and the four one, for example, coronal discharge. This physics interface is predefined multi-physics coupling that automatically adds all the physics interfaces and coupling features required. ACDC interfaces. The AC/DC branch chapter describes the two physics interfaces available with this module under the AC/DC branch of the model result. Many of the plasma interfaces already solve Poisson's equation, and volume and surface charge are automatically accounted for. This means that the electrostatic interface will rarely need to be used. The next one is fluid-fluid interfaces. The fluid-fluid branch describes the laminar flow interface, which has a few additional features available for this module compared to the basic license. The next one is Boltzmann equation, two-term approximation interface. The Boltzmann equation Total approximation interface computes the electron energy distribution function, or EEDF, from a set of collision cross sections for some mean discharge conditions. The interface can be used as a preprocessing stage before solving a full space-dependent model. The main purpose of this interface is to compute electron source coefficients and transport properties. The next one is drift diffusion interface. The drift diffusion interface is used to compute the electron density and mean electron energy for any type of plasma. A wide range of boundary conditions are available to handle secondary emission, thermionic emission, and wall losses. This interface rarely needs to be used by itself as it makes up part of the application-specific interfaces described later. The next one is charge transport. The charge transport interface computes the density of charge carriers in a background gas under the assumption that the transport is dominated by migration. This is typically only used as part of the corona discharge multiphysics interface. The heavy species interface. The heavy species transport interface solves a mass balance equation for all non-electron species. This includes charged, neutral, and electronically excited species. The interface also allows you to add electron impact reactions, chemical reactions, surface reactions, volumetric species, and surface species via the model builder. This interface rarely needs to be used by itself as it makes up part of the application-specific interfaces described later. The chapter of application-specific interfaces. The Plasma module provides four application-specific multiphysics interfaces for modeling and most common types of discharge. The first one is plasma, the next one is plasma time periodic, and the next is inductively coupled plasma, and the last one is inductively coupled plasma with radio frequency bias. The first one, plasma. The plasma interface can be used to model positive columns, BDB, discharge, Gauss discharge, CCP reactors, and coronal discharge. The complicated coupling between the electron transport, the heaviest species transport, and electrostatic field is handled automatically by the software. Furthermore, the secondary emission flux from a ion bombardment on an electron is automatically computed and used in the boundary conditions for electrons. The next one is plasma time periodic. The plasma time periodic interface can be used to model capacitively coupled plasmas. Instead of solving the problem in the time domain, the periodic steady-state solution is computed. This avoids having to solve for tens or hundreds of thousands of radio frequency cycles, which is typically how long it takes before the plasma reaches the periodic steady-state solution. This approach maintains all the nonlinearity of the model while dramatically reducing computation time. The physics interface accomplishes this by, attaching an extra dimension to the underlying mathematical equations representing on radio frequency cycle and enforcing periodic boundary conditions in the aforementioned extra dimension. The third one is inductively coupled plasma. The inductively coupled plasma interface can be used to model discharge sustained through induction currents. Discharge typically operate in the megahertz frequency range. Inductively coupled plasma (ICP) are important in plasma processing and plasma sources because the plasma density can considerably higher than an capacitively coupled discharge. Inductively coupled plasmas are also attractive from the modeling perspective because they are relatively straightforward to model due to the fact that the induction currents can be solved for in the frequency domain. This means that the Faridi frequency cycle applies to the driving coil doesn't need to be explicitly resolved when solving. As such, the closest steady state solution is reached in relatively few times steps. The next one is inductively coupled plasma with radiofrequency bias. The inductively coupled plasma with radiofrequency bias interface can be used to model discharge sustained to induction currents and that have a periodic radiofrequency biased electrode. This interface uses the plasma time periodic interface to solve the periodic steady state for the radiofrequency biases. The inductive currents are solved in the frequency domain as in the inductively coupled plasma interface. This type of discharge are interesting, yeah, because the plasma density and the ion flux at a surface can be controlled somewhat independently. Thank you so much for watching my tutorial video until the end, and also you can download the appropriate and proper computer simulation from github.com/masterscript. Today is 17 of March 2026. Time is 9:17 at night, and I wish that you can use my this tutorial video.